Hello and welcome to another episode of Low Pressure Area, a Campbell Scientific podcast with me, Jamie McDonald.
And with me, Richard McKay.
Again, it's that time of the month, Richard, where we're chatting about all things meteorology and weather. And in this episode, we are covering perhaps one of the most important parameters when it comes to weather and meteorology, and we'll talk a little bit more about why that is later. And it's temperature. Temperature is what we're looking at today, and we're going to be talking about really what is temperature to begin with. And then, since this is a podcast from Campbell Scientific, we'll be talking a little bit about the measurement of temperature as well and the different ways of doing that and its history. And then at the end, we'll be talking about supermarkets, of all things. And you'll have to listen to the end to figure out what supermarkets have got anything to do with temperature. Now, before we get to all of that, I think useful for us to say that this is a new podcast for us, and we're trying out different topics and different themes to get an understanding of what you, our audience, are really interested in. So we've covered forecasting, we've covered clouds. Today we're looking at temperature, but we'd really like to hear from you what it is that you would like to hear us discuss in the future. So make sure to put any ideas in the comments below the video or reach out to us directly. And of course, remember to like and subscribe so that the next episode comes straight to you as soon as we've launched it. We'd also really like to do a question and answer with you guys at some point. So if you have any questions that you'd really like us to answer, again, please do make sure to put those in the comments. But let's get straight to it, Richard. Temperature. What is it? I mean, let's start from the very basics. How do you define temperature?
Yeah, it's a really good topic, one I could certainly talk for a long time. And, as we agreed, we'll try to keep this one a bit shorter maybe and a bit more of a quicker tempo, hopefully for a general knowledge, and then we can dive into lots of different aspects of this in future episodes. But I'll just share some slides that I had prepared here. Again, as in the past, this one's slightly different branded format, but content still be the same. The definition, according to dictionary.com and a number of different sources, and this one I particularly like because it wasn't trying to get too specific. Sometimes they try to relevate it to, let's say, the type of concept where you're saying is the temperature of a fight or an emotional state, but this was much more relevant to our purposes here. So a measure of the warmth or coldness of an object or substance with reference to some standard value. And I like that because it didn't reference particularly a particular scale of temperature, whether that be Kelvin, Celsius, or Fahrenheit, or some other one. And it also just says a measure of the warmth or coldness. And so it's not measuring at any particular point either. And maybe just to clarify, there's, obviously different places that you can measure, and that could be a whole other aspect to one of these. And you say that temperature of two systems is the same when the systems are in thermal equilibrium. And why is that important? You'll see in a future slide. So that's what temperature definition is. I'll maybe continue quickly on and say where's the history of the word, which we were doing as well. And so the etymology of the word is deriving from the term temperatura, meaning a moderation. And that was referencing human body temperature because originally a lot of concern was around the medical conditions, so fever and things like the plague and whatnot. So it's certainly in earlier times, mostly deriving from that interest, and not my area of specialty, but how the body temperature varied and trying to understand that better. So that's sort of the first 2 points, I guess. Back to you, Jamie.
Yeah, and interesting. And I like this, that we've been looking at the etymology of these words as well, because it's really interesting to see where they come from, and they're not always from the same period of time, obviously, or from the same language. So this temperatura is Latin originally, right? So we're talking a long time ago, at least in the scale of human history, when we were talking about this and interested in it. Yeah. If we talk about I know you mentioned Celsius, Kelvin, and Fahrenheit there when you're kind of giving the definition. These are all three different measurement scales, I guess you would call them, that we use to give some sort of indication of where a temperature is on a scale, right? So that it means something to us. Where did those come from? And which one came first? It was Fahrenheit, I think, wasn't it?
Indeed, it was. So I'll come back to this slide a bit later, but to go sort of a bit of a timeline for temperature, and boy, you can certainly spend hours in this area as well, I found. And I've linked to a paper, we'll put that in the comments as well. There's a chap at the National Physics Lab in the United Kingdom that published a paper which I've put the title up in the upper right, and obviously, you know, has the respective copyright and ownership of the owners and the publishing house. But it was really talking about the evolution of temperature measurement. And so I borrowed some points from there, but some points from Wikipedia, some points from other sources, of course, as always. But the first ones I want to say related to sort of air temperature, really, which tends to be what we talk about, ambient air temperature. When we're talking about temperature here, there are certainly other ones. But 1590, I was really surprised it was quite that long ago. Galileo Galilei was the one for the thermoscope. And then there was various iterations refining that and trying to deal with some variances of it. 1654, and these are ones I've taken from the web. Somebody hopefully will, you know, tell me if I've got them slightly wrong, but with the best, you know, knowledge, this is what I came up with. 1654 was the first modern thermometer, which was alcohol in the sealed tube. So believe it or not, those were still used back when I was observing on an airfield in the late 80s, early 90s. And still to this day, sometimes are used because they're used for minimum and maximum temperatures. And they tend to check when is it good, that the way that the air and the pressure works is it'll move it along and it'll stay at the lowest point, doesn't come back and, you know, have that variability in some cases. So they're particularly good for maximums and minimums when you don't have digital systems or analog ones going into data loggers or some other data acquisition system. So and then I'll jump over the Fahrenheit and Celsius for a second, come back to you in that question and a point in a second. But 1714 was when the first mercury thermometer came around. Again, sort of same concept as so partially filled with alcohol, but it was with mercury, and that was much more repeatable. Obviously not very environmentally friendly. And mercury thermometers, quite honestly, were still being used in around the world today in some national weather services. They're fantastic measurement device, but they obviously have that environmental aspect. So slowly, the World Meteorological Organization that we've talked about in the past is trying to phase out a lot of these older technologies simply because of the environmental aspects of them. And so you also have to understand when you're changing from one to another that you need to really see where where does a change happen. So when you introduce a new technology, a new way of measuring something, you need to see how does that change your data. Does the temperature you're measuring at 7.4 all of a sudden become 7.9 because of the new technology, or it's not quite that dramatic, but there can be small step changes in the measurements, and you have to understand those and run them side by side to really understand how that difference happens. And then the current technology that we're using, something called the PRT thermometer, which we'll talk about a bit later, was invented in 1885. And to be honest, that's the thing that we're using today, really. There are all sorts of other ways that we're measuring in addition to that, but that's for ambient air temperature that's on most weather stations. That's typically the concept that's being used.
Which is pretty wild in itself, right? That the current technology came out in 1885, but we'll come back to that.
Yeah, that, like you said, another whole topic on itself. Fahrenheit, though, you're right, did come out first around 1700, and it had 3 points apparently that were used. I didn't realize that until I was researching for this talk. And the two that are much more, let's say, robust in terms of their, you know, the quality of that measurement is the 96 degrees Fahrenheit body temperature, and then 32 degree Fahrenheit mix of ice and water. So where that's the 0 degree sort of equivalent Celsius line and melting. And then the author of that paper I'm talking about here was suggesting that this brine mix of ice, water, and salt at 0 degrees was sort of the minimum point, but it originally wasn't maybe as robust scientifically as it could have been because there wasn't maybe as well-defined mixture ratios in those. So, but nevertheless, you know, 0 to call it roughly 100 scale, and then Celsius came along a little bit later in 1741. Interesting, I again didn't remember this. I'd read it somewhere in the past, but the scale was originally inverted. So 100 degrees Celsius was actually where the melting point of ice and was at, and boiling was at 0 degrees Celsius. So It was only a couple of years later that, unfortunately, I think Celsius passed away in 1744, and a Swedish chap, I don't reference his name here, but he, botanist, I believe, interestingly, said in 1745 we should reverse that and have obviously 100 degrees as the boiling point of water and 0 is the melting point. So yeah, not too far apart from each other, but quite a long time ago, and Kelvin come around as the scientific SI, scale that we use to relevate everything, and that has a much wider range, I'll suggest. I'll have to look at that one and see if I can get more facts on Kelvin, and maybe talk about it with a bit more knowledge the next time we talk. But that's a bit of the timeline and the difference between Fahrenheit and Celsius.
Yeah, and I mean, interesting, of course, that both of these were, 1700s, and we still around the world haven't agreed on which one we want to use. I mean, we're working for a company that has its headquarters in the US, and of course, in the US, Fahrenheit is still by far the most dominant scale used. We're both, Richard and I, in Europe, and Celsius is the way. I mean, looking at this, 96 Fahrenheit means nothing to me. So it's quite amazing that they're measuring the same thing, but in a slightly different way. Just on thermometers though, right? So we've talked about here, there's thermoscopes, and then the kind of more modern thermometer in 1654, and then the mercury thermometer, and then the one that we're using most today, this PRT. Do you want to just tell us a little bit about that? And
sure. Yeah.
What it actually does?
So interestingly, one of the things that we haven't talked about maybe is another point for discussion in a future podcast would be what you're measuring, and is it representative? So the fundamental thing that we're trying to do is be representative of anything you're measuring. So if you're measuring air temperature, you want to measure the air, and you don't want it to be unduly influenced either by mechanical design, by something else that's going to change the way that you measure that, or that it's really accurate, really. But the term representative means that it's used to denote, is it at the right height? Is it the right quantity, the right quality of the measurement you're making, whether that be temperature, humidity, or the clouds or something else. So representativeness is hugely important. And ideally, you'd make a temperature measurement of air without actually being in that air, and so you'd have to remotely measure it, sample something through it, with some type of concept like a sound wave or laser or something else, but you might actually warm it up doing that. How do you make sure that it's accurate? What time scales, averaging, all sorts of questions that come into that. But anyway, I'll rein all this in and say the PRT stands for platinum resistance thermometry, and the current methodology that we do is we span a very thin, very sensitive, very small amount of platinum wire across 2 points, and we send electrical current through it. And what we're looking at is actually the amount of loss of that signal as wind goes past it and cools that wire effectively. And so the wind just makes it less efficient, and it loses some of that energy, and there's a really good correlation between that. So you would measure this electrical current going across very small, maybe roughly a centimeter at most, sort of span, and you would look at that and can correlate it back to temperature very well. The challenge is, of course, that you need to protect that so that it's not unduly influenced by wind, rain, or sun, because sun hits it, it warms up. If the rain hits it, it sort of acts as a damper on the latency of the measurement. Wind would obviously cool it inordinately, so you want it to be representative of your environment. So if you have 5-meter wind, maybe 7-knot wind or 2 mile per hour, whatever the number might be, and the scale you're using, you want it to be measuring roughly that wind rather than being shaded behind a building, or to be exposed unduly to a very large turbulent structure, maybe because of the way the flow is going around an urban area. So those are the points, but it's a platinum resistance thermometer, and nowadays it's digital, whereas in the past it was analog.
Yeah, exactly. And I think you had a picture, didn't you, or an example of what these look like these days, or could look like. And here is again a quick cheeky plug for Campbell Scientific, where we are. an example of a PRT. This is our TempView digital thermometer. With as you've got there, Richard, a non-aspirated shield around it. And, when we talk about measurements and shielding, this is a whole different topic in itself, so we won't go into it there. But to give a kind of example of size, you said the piece of platinum there is kind of a centimeter long. And I think that whole sensor, people looking on screen, it's maybe 10, 15 centimeters max in length.
Correct.
So
yeah,
not
right.
terribly big. Yeah.
And that's really from that bottom white bit just above the cable all the way up to the top of, I don't know if people will see my mouse on here if they're watching, but there's a very thin metal rod extrusion here from the plastic housing. And this is, again, a whole topic about having that as thin as possible is really important so that you're very sensitive to change. So that platinum resistance thermometer is in the tip of that, but you also can't have it so thin that it breaks. And, again, the problem. But this shield is, like you said, just trying to make a tortuous path so that you get some ambient air through and that you're still making a measurement as representative as you can. But it's obviously, that's not air. It's not it's being hugely influenced by the mechanical design, but I mean, this is still very, very good. There are all sorts of other concepts, but nevertheless, this is sort of when you see sort of that beehive structure on some of the weather stations as you drive around the motorways or different places, then that's what's inside of one of these is temperature and possibly humidity as well.
Yeah, and hopefully not bees in there, but you never know. Sometimes they do manage to get in.
And insects are a real challenge in any measurement. So
they are absolutely. Look, I know we wanted to keep this episode a little bit shorter today, so I think we'll wrap it up here. And hopefully this has given you all a kind of very brief overview of some of the important parts of temperature, where it's come from, and where we are today. We're going to wrap up this week's episode with a new section that we'd like to introduce in every episode, which we're calling the fun fact of the month, for lack of a better name. And this is where we come back to the supermarket. So Richard, supermarkets and temperature, what's the link?
So temperature is something that's actually fairly, dare I say this, easy to forecast and doesn't provide as much of a challenge as some other parameters. And the link to supermarkets, which a lot of people may not be aware, is supermarkets employ meteorologists, the same as insurance companies do. Even large sort of candy suppliers or chocolate bar manufacturers will employ meteorologists. And what they're doing is the supermarket link is they will be looking out a week or even 2 weeks to make sure that they have the logistics in place to get either barbecue food, the aprons, the tongs, everything you need, the charcoal, to enjoy that sunny weekend that could be forecast in 2 weeks' time, or alternatively, if it's going to be really miserable weather, depending on your viewpoint, but cloudy and rainy and whatnot, that there could be the exact opposite, some really nice, warm comfort food sort of type of things, and maybe different types of things that we buy. And we are definitely creatures of habit. So the supermarkets will actually employ those meteorologists or subscribe to forecasts where they will forecast out 2 weeks and then make sure they have the logistics in place to get that to the supermarket at the time, just in time. And then, believe it or not, they'll actually, from what I've understood, they'll place equally sort of a liability guarantee on the opposite happening, so that they expect that to be barbecue weather, for example, in 2 weeks' time, and they'll make sure that they get all the barbecue stuff to the stores. But should that go completely wrong, then they'll have insurance in place to make sure that does that happen, that they haven't lost everything. So those are where the meteorological aspects come into it, and really quite an interesting aspect of meteorology and forecasting in its own right.
Yeah, absolutely. Well, there you go. So next time you're in the supermarket and it's a lovely sunny day and you want to buy something for a barbecue, it's no coincidence that the supermarket has that ready for you. They've planned ahead. Amazing. All right, Richard, I think we'll leave it at that for today. So thanks everyone for listening. Remember to like and subscribe so that you get the notification when the next episode comes out, and we'll see you next time.
Thanks, everybody.